Hey y'all, Kyle at Myers Mathematics. How y'all doing today? Excuse me, getting over a little bit of a cold here, so you have to bear with me. Got just a little bit of a lingering cough, but not going to stop me from talking about something really, really cool. Number systems. Okay, so it sounds maybe kind of boring if you're not into math, but have you ever seen a problem and you're just like, oh yeah, all the real numbers. Sure, okay, I'll just solve and get an answer and I'll just ignore the fact that I don't know what a real number is. Or integers, right? You see that word all the time. What the heck is an integer anyway? Well, let's talk about what that means. So, let's start with what we're going to do today is we're going to start with the smallest number system and then work our way up from there. And we'll even talk about a few that you won't know about at all unless you were a weird math nerd like I am. Weird math major, math ed major, whatever. Not even math ed majors learn about this. Really just not until you're really so far into the maths that you just use letters instead of numbers. Whew, crazy. So that's what I'm going to dive into today. MyersMathematics.com. That's what we're doing. Let's jump in. So the first number system, all right, natural numbers. Natural numbers. Okay, so natural numbers is the smallest number system that I know of. If you can think of a smaller number system than the natural numbers, let me know in the comments. 1, 2, 3, 4, 5, all the way to infinity, right? Not including infinity, obviously, because infinity is not a number, right? So note, infinity is not a number. Let me see if I can change my color here. I'm going to use galaxy. Note, infinity is not a number. All right, didn't know if you knew that, but if you didn't, if you thought that was a number, it's not. Somebody lied to you. I'm sorry about your troubles. So natural numbers, 1, 2, 3, 4, all the way to infinity. Not including infinity, of course. Okay, that's the first one. That's the easiest. You probably haven't heard of this one because people hardly ever talk about it. But this is one that you have definitely, most likely have heard of, called whole numbers. Whole numbers. All right, I'm going to kind of just add this off to the side here because really it just add 0. Yeah, that's it. You just add 0 to that and then you have whole numbers. All right, so what I mean by putting a 0 here is that whole numbers is not just 0, right? Whole numbers, let me use a slightly different color actually to help with this. So let me use purple. Let me change to purple here. Right, so whole numbers is also all the natural numbers, meaning whole numbers is 0 and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? All the way to infinity. You've probably heard of that, whole numbers. In a problem, they'll be like if you want to deal with fractions sometimes, they'll be like, find out if they're divisible, if the whole numbers that make up the fractions are divisible or something like that. Right, so you've probably heard of whole numbers. That's typically the numbers that you deal with. Actually, you start with natural numbers. When you first learn about numbers, you start with natural numbers. They don't call them that, but you don't really learn about 0 until you're, kindergarten-ish, depending on what state you're from. And then they introduce the concept of 0, right? Because it's kind of, when you're really little, the concept of 0 is kind of hard to wrap your mind around. But then eventually you grow up and you're like, oh yeah, that kind of makes sense. All right, this is the one that you guys have definitely heard of if you are at least in third grade or so, right? So now we've advanced to third grade. Natural numbers, that's like pre-K stuff, and then whole number, you're talking about like kindergarten-ish integers you learn of by the time you're in, I don't know, third, fourth, fifth. You start talking about negative numbers, right? Numbers can be negative. Right, so integer, numbers, right? So that would be like dot, 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 all the negative numbers. -3, -2, -1. No fractions or decimals yet, right? So I'm not including 0, right? Because 0 is the whole number, right? So integers is all the natural numbers and whole numbers as well, right? So it's sort of like this is all encompassing right here, right? It's got all these numbers. So integers is all the negative whole numbers, all the positive whole numbers, and then 0, right? All the counting numbers. So that's it. That's all integers really are. So whenever you see integers, they just mean positive or negative whole numbers, right? Positive or negative whole numbers. And actually, let me make a space for that. Let me make a space for this. Right? So natural numbers, right? So basic counting numbers. Basic counting numbers. That would be how I would define it. And I'm not using a technical definition here, so if you're a serious mathematician watching this video, I'm not trying to use a formal definition here. If you want a formal definition, you can Google it, just like anybody else. Whole numbers, right? So basically the same thing. So counting starting with 0, right? And then for integers, for integer numbers, whole number, natural number, integer number, it's just going to be, a lot of times people call it positive or negative whole numbers, right? Because whole numbers include 0. So if you just say positive or negative whole numbers, right? 0 is not technically negative or positive. It's the one number that's neither. It's the boundary between the positives and the negatives. That's integers. Now, what comes after integers? You're like, well, when are we going to talk about fractions and decimals? Right now. Right now. Let's change to red for this one. So then you have rational numbers. Rational numbers. Okay, so this one's actually a little bit more complex. Now I'm only going to put you know what? Let me just write it. I'll just write it A over B. Okay, so this is kind of the definition. A over B. So anything over anything else where A and B are integers, right? So it could be 1/3. It could be -2/5. It could even be any of these other numbers, right? So natural numbers, you can write any natural number as like 1 over 1, 2 over 1, 3 over 1, and then integer numbers, right? -3 over 1, -2 over 1. If you can write any of those numbers over 1, then now it's a fraction. So now it's rational. And numbers like 0.2. Why? Because 0.2 can be written as a fraction, right? Or 0.3 repeating, which is equal to 1/3, right? So if it repeats, you can write it as a fraction. Any repeating decimal you can write as a fraction. And any decimal that ends at some point can be written as a fraction, right? So that's all the rational numbers. I have to like scroll out to get it all in here now. I'll have to do this even more as I go along. So that's a really big number system, right? It's like really, really big. It's like a lot bigger than all of these number systems put together, the integers. It's much, much bigger, right? It's hard to talk about how much bigger it is because they're both technically like never ending. So I won't get too much into that because that gets like really technical really fast. Rational number. So definition-ish, right? Not a formal definition, but a rational number is basically just any number that can be written as a fraction, right? So any number that can be written as a fraction. That's it, right? Can be written as a fraction. So I already showed you that it's like a over b, a and b have to be integers. That's kind of more technical, but basically any number that can be written as a fraction. So it doesn't have to be a fraction. It can be a decimal, it can be a percent, it can be a whole number, it can be an integer. Those are all rational numbers. Okay? And you can actually put square roots in there to some degree, right? Square root of 4 is rational. It's also an integer, a whole number, and a natural number because the square root of 4 is 2. So if I take the square root of 4, I get 2. So that means that it is, square root of 4 is rational. But if I can't take the square root, irrational. If I cannot take the square root, right? So then any, and I'm going to add in real at this point. So we're going to talk about real numbers in a second. So any real number that can be written, that cannot or can't be written as a fraction. This is where you get into some fun numbers like pi. Ooh, pi. Ooh, and if you really like pizza, tell me what your favorite pizza is in the comments. My favorite pizza is probably mushrooms and maybe some pineapple and mushroom. I don't know. What do you guys think? Tell me in the comments. Irrational. Right, number systems are getting real big now. Irrational numbers there's actually more irrational numbers than rational numbers, believe it or not. So this is the first time that the number systems are not overlapping. So this is like the square root of 2, right? Or the square root of 3. Not the square root of 4, right? Because the square root of 4 is 2, right? That's just a natural number. But any square root that can't be simplified, also numbers like pi, right? E, you might not have heard of E yet, depending on what grade you're in watching this video. All right, so rational numbers, you've heard of fractions by the time you're in middle school-ish math, depending on where you are, of course. Then irrational numbers, you actually don't hear about until probably the first time you find the area or the perimeter of a circle, right? Because you have to use pi to do that. Right, so actually irrational number system should be bigger. So let me make this like big, right? So this is actually really big. Irrational number system is bigger than the rational one. And then if you just put them together, then you get real numbers, right? So that's probably the one that you've heard of the most. So let's zoom in on this here. Real number. A real number is pretty much all the numbers that you need to deal with up to a certain point. So it's basically just any number. So it's all the rational and irrational numbers, right? Now there's no real number that's not rational or irrational, right? So for instance, what I mean by that is like a rational number could be just a rational number and not an integer. But a real number is either going to be rational or irrational. Okay, so there's no examples of real numbers that I could show you. That would be, you get a different color here. Let's use pink or something maybe. Plum. So I'm going to show a little bit of overlap here, just so I can write the word real, but there's no overlap. There's not really any overlap here, right? There's no real overlap. No real overlap. So real numbers. There's no number that's a real number that's not already irrational or irrational. So that's it. No examples of real numbers that I haven't already talked about. But there's one more number system that I'll talk about here called, actually two more, sorry. imaginary, which will lead me to the last number system that I'll talk about, and then I'll mention maybe a few others that you probably won't ever deal with unless you just really, really, really love math. So an imaginary number is basically it's AI. So what does that mean? So A is a real number, and then I, and if you've seen I before, you know what I'm talking. It's the square root of -1. So it's actually going to make more sense when I draw this. All right, so it's going to make more sense when I draw this. I'm going to zoom out a little bit more this way. And we're getting into some crazy stuff now, so let's use some crazy colors. All right, small interruption here. But if you didn't see me write this thing here, imaginary, I'm using a crazy color for this. Imaginary numbers, because I've only got two more that I'm going to talk about, right? So I'm almost done. Imaginary numbers, we're going to have anything that is, and I put a little curve on my eyes just so it doesn't look like a 1. So if you're wondering what that is, it's the letter I, lowercase. It's a lowercase I, right? So the square root of -1 is the definition of what I is. So any imaginary number is just something times the square root of -1. So for instance, the square root of -4, because this is just the square root of 4 times the square root of 1. So it's 2i, right? Or it could be like the square root of 2 times I, right? So any real number multiplied by the square root of -1. So it could be a lot of different things. Okay, but imaginary numbers are not real numbers. They're imaginary, right? It's real, and then there's imaginary. Now, this is the part where it gets real fun, and I'm actually going to use a different illustration to show how the real numbers and the imaginary numbers come together to make complex numbers, right? So, complex number, right? So a complex number is always going to be in a special form, a plus bi, right? So if you're a younger person and you're watching this video, this is how crazy the math gets, right? This is the wormhole. It's just the math oblivion, okay? Math gets really crazy the further you go in, but it's really, really cool. So check this out, a plus bi, a and b, right? So those letters are representing, a and b are real numbers, okay? So a and b represent real numbers, and then of course I is the square root of -1. Okay, and I'll draw that as well because it doesn't look as nice when I type it. So I'm going to use my Venn diagram-ish, my approach that I've been using here, and then I'm going to show you another way to look at complex numbers. That's really, really cool. So actually, probably need to zoom out even more for this. So I'm going to use my galaxy pen for this. And let's increase the thickness on it. So complex numbers. Complex numbers. All right, so a plus bi, where a and b are real numbers, and then of course I is the square root of -1. Okay, so basically anytime you take the square root of a negative number, it's going to create an imaginary number, and then a is any real number. So I can actually take this, all of this, and go all the way around, right? So now there are complex numbers. So remember when I have real numbers, if it's a real number, it's either going to be rational or irrational, right? There's no real number that's not irrational or irrational. It's rational or irrational. But with complex numbers, you might think, oh, it's just something that's either real or imaginary. No. If it's just, if b is 0, right? So if b is 0, then you have a real number. If a is 0, then you have an imaginary number. But you have a ton of numbers that are complex, and they are neither real nor imaginary. So check this out, 2 plus 3i. That's not a real number, but it's also not an imaginary number, because an imaginary number has to be just a non-real number. It's some multiple of the square root of I. It has to have the square root of I in it, right? But this 2 plus 3i, that can't be written as an imaginary number. That's just straight up complex. Okay, so before I show you a visual of what it looks like to have a complex number, let me zoom back in on here. Right. Back in. There's actually a couple other number systems that I wanted to point out real quick if you really want to know what else is out there. There's, forgive me if I spell this wrong, quaternion numbers. All right, so I'm just going to put crazy. I'm not even going to define it, right? Because I don't fully understand it myself. I had never delved into the numbers that crazy. But there's a quaternion, right, which is the first number system that comes after complex. And then I believe the next one is, let's see, octanians. It's like octanians or something like that. Octanian. An octanian number. Or no, octonian. Octonian. I wonder if it's going to spell check that. Oh, it doesn't. Oh, yes, it does. Okay. Right. Well, spell check. You got it wrong. Because I'm pretty sure that's how that's spelled. Octonian number. It's an ultra crazy, right? Ultra crazy number. So this is just, it goes, just the rabbit hole goes deeper and deeper. That's all I got to say about that. But let me end with another visual of what a complex number can be written as to make some more sense of this. All right, so before I do that, if you want to see a particular video on something, right? If you want to see a particular video on something, then let me know in the comments. I would love to hear what you want me to talk about. Maybe you have a specific problem, specific math problem you want me to work out. Or maybe you just were wondering about a topic and you weren't sure how to go about it, or if you were wondering if there's like a trick method to something. Right? I have a trick method for pretty much everything. Okay. So if you are wondering about that, if you have any questions, if you want me to do a video on a particular topic, just let me know in the comments. I'll look through those and periodically and create some videos based on what you want to know. So if you are familiar with what this is, right, the x-axis and the y-axis, right, if you're graphing lines, so if you're an algebra student or higher, you know what this is. The x-axis, the y-axis, you graph lines, you graph parabolas, cubic functions, etc. Now, let's say the x-axis represents the real numbers. Okay, so for instance, this right here could be 3, 0. Okay, that would be a real number. Right? Now let's say the y is imaginary. The y is an imaginary number. So for instance, 0, 3 I. We'll just throw an I in there. You don't have to, because we already said it was imaginary numbers. But just so you can see my point here. So if you look at the x-axis, every real number can fall on that line. We can put every real number on this line, right? So like the square root of 2, it would be over here somewhere, right? If 3 is right here, then 1 would be about right here. So it would be like somewhere in between-ish. And then same thing with imaginary numbers, right? So if I wanted like the square root of 2 times I, that would be down here somewhere, right? Roughly the same distance that it would be if I wanted the square root of 2 on the line. But that's just things that are on these lines. See all this space? All this space out here? All of this space represents things that are complex. Complex, but not real or imaginary. Right? So all of that space is all complex numbers, and only the things that are on the x-axis, the horizontal line, all of those things are real, and all the things on the vertical axis, the y-axis, all of those represent all the imaginary numbers. So there are a crazy amount of complex numbers. And then, of course, there's number systems after that. It's just mind equals blown. But that's my visual. Here are all the numbers that you'll ever need to know about. If you want to graduate, high school and do something not related to math, you'll never need to know anything beyond complex numbers. Because you learn about complex numbers maybe in Algebra 2 and whatnot, but you'll never really use them too much. But if you were wondering in your math problem what they mean by complex, imaginary, irrational, real, rational, natural, integer, whole number, that's what they mean. All right, this has been Mr. Kyle at Myers Mathematics. Closing down.